So hi everyone, welcome to this channel. Today we're going to look at basic electricity. You are still on Best Science Brain YouTube, and if you are not subscribed to the channel, kindly subscribe to the channel by pressing on the subscription button, and then also you can still share our page to people for them to subscribe to the channel. Today we are looking at the second phase of this topic. We have done the first video on basic electricity, which is meant for students in senior secondary 3, SS3, and also for those in SS2. So today we're going to the second part of the video, basic electricity. First of all, today we'll start by, first of all, revising or summarizing what we learned before about resistors. Resistors in series. When you have the resistors connected end to end, you have resistors in series. For instance, let the resistor have resistance of R1, R2, and R3. They are in series. And whenever resistors are in series, the same amount of current will flow through them. So let the current entering from the circuit be I. Current passing through R1 is I1, passing through R2 is I2, passing through R3 is I3. So when resistors are in series, the same current will pass through them. That means I will be equal to I1, also equal to I2, also equal to I3, which is still come out at the same current. So one important thing to note is that when you have resistors in series, that the same current will flow through each of them, irrespective of the value of the resistances. Then the potential difference or the voltage across each of them, let the voltage across R1 be equal to V1, across R2 be equal to V2, and across R3 be equal to V3. So, will the potential difference across each of them be the same? No. So when they are in series, the current across them remain constant, but the potential difference across them will be different from each other. So the potential difference across the first resistor will be different from the one across the second resistor, will be different from the one across the third resistor. They will be different from each other. But the total potential difference from the end A to the end B, the total ED, will be the sum of the potential differences V1 plus V2 plus V3. And I hope we know how to define potential difference. Potential difference is the work done in taking a unit positive charge from one point in a closed circuit to another point. The work done in taking a unit positive charge, that is a charge of one coulomb, from one point in a closed circuit to another point, what is meant by potential difference. So when you have resistors in series, the current flowing through each of the resistors remain the same. I1, I2, I3 that is equal to each other. But the potential difference between across each of the resistors remain different from each other. That means V1 will be different from V2 and also different from V3. So as you can see our diagram from the illustration, current I1 equal to I2 equal to I3, the current remain the same, while the potential difference V1, V2, and V3 will not remain equal, they will be different from each other. But the total potential difference will now be equal to V1 plus V2 plus V3. We now define potential difference as the work done in taking a unit positive charge from one point in a closed circuit to another point. We're going to look at resistors in parallel now. So we'll have resistors connected in parallel. In parallel, that is when their ends are joined to the end A and B respectively. Okay? The resistance of this one be R1, R2, and R3. Will the same current flow through each of them? The answer is no. Let's assume that this is the current coming out from the battery. At this junction, the current will break into paths I1, I2, and I3. So when the resistors are connected in parallel, the same current will not flow through each of them, except if the resistors have equal resistances. That means I1 will not be equal to I2, will not be equal to I3. But the current I will be equal to I1 plus I2 plus I3. So when you have resistors connected in parallel, they will take different amount of current. Assuming that R1 is 2 ohms and R2 is 3 ohms and R2 is 3 ohms, then R3 is 4 ohms. Which of them will collect, or which of them will take the least amount of current? The one that will take this amount of current is R3 because it has the highest resistance. While the one that will take the highest amount of current will be R1 because it has the lowest resistance. So unlike a serial connection, when resistors are connected in parallel, the current flowing through each of the resistors will be different from each other. The only condition when they will be equal to each other is when the resistors have the same resistance. But as long as the resistors are different from each other, different amount of current will flow through each of them. Then what would they have in common? The only thing they can have in common is that they will have the same potential difference. V1 will be equal to V2 will be equal to V3. So when you have resistors in parallel, they will have the same PV across each of them, but different current passing through each of them. So this is opposite to the situation we have when they are in series. When they are in series, the same current will pass through each of them, but when they are in parallel, different currents will pass through each of them. When they are in series, they will have different potential difference, PD, and then when they are in parallel, they will have the same potential difference across each of them. So what it means is that from Ohm's law, since voltage is IR, what it means here is that I1 times R1 will equal to I2 times R2 equal to I3 times R. Since the difference is current times resistance. So you apply I and I get V1, I2 and R2 get V2, I2 and I3 and R3 get V3. So when they are in parallel, this holds. They have the same equal potential difference, but different amount of current passing through each of them. Problems. We're going to take a lot of problems on this basic electricity, and most of these problems we're going to take will all be from past examination bodies, WAEC examination, GCE, and then JAMB examination. So the first problem we'll take, we have this situation. 2 ohms, 3 ohms, 4 ohms, 2 ohms, 3 ohms, and then 4 ohms. Question says you have to find the combined resistance of the above diagram. So find the combined or the equivalent resistance of the above diagram. To solve this problem, we have to recognize that we have to find how the resistors are connected. These resistors are connected in parallel. So we have 2 in parallel, and we have 2 in series. So when you want to solve this problem, the first thing you have to do is to combine the resistors in parallel. That is these first 2. And I gave you a short form of finding the resistance, the equivalent of resistance in parallel. What you do is use the formula R total, which is R1 times R2 all over R1 plus R2. So when you have 2 resistors in parallel, the only way you combine, instead of using the reciprocal formula or using 1 over R, equal to 1 over R1 plus 1 over R2, you can use this shortcut. So that gives us, there are 2 ohms times 2 ohms all over 2 plus 2. So that will give you equal to 2 times 2, which is 4. 2 plus 2 is also 4. So when you add, divide, you're going to get 1 ohm. So you can look at it. 2 ohms times 2 ohms, as you have it there, all over 2 plus 2. That will give you 1 ohm. So we are combining these. So when you are combining the ones in parallel, we now have everything in series. This is the 1 ohm, which is obtained by combining these 2 in parallel. This is 3 ohm, and this one is 4 ohm. So everything now appears to be in series. You then add them together, and now have 1 plus 3 plus 4. That gives you 8 ohms. That becomes the net or the equivalent resistance, the answer to the question on the board. So you can go through our work and see that it is correct. So we'll take another problem also from JAMB examination. We have this given to us. Two ohms, 2 ohms, 2 ohms, 1 ohm, another 1 ohm. We are asked to find the net resistance or the equivalent resistance of the arrangement above. Look at this problem. How to solve it? We have to first of all understand the diagram. Look at the diagram very well. You see that we can see that this one, R1 and R2 are in parallel, but they are facing each other. They are in parallel. So we can take the total resistance of R1 and R2, can call it RT, which is R1 times R2 all over R1 plus R2, which is going to be 2 times 2 all over 2 plus 2. and that will give you 1 ohm as our answer. We go back to the diagram. You see that this one, R3 and R4 are also in parallel. We find the total resistance of R3 and R4 because they're in parallel and only two. We can still use R3 times R4 all over R3 plus R4. That gives us 2 times 2 all over also 2 plus 2. And that will still give us the same 1 ohm. So we are joining these two in parallel. We also join these two in parallel. Then what of these two? In what way are they connected? These two, are they in parallel? No, they are in series because this place is open. There's no wire here. So these two are in series. So total becomes, now have 4 buses to draw. The 4 buses. What are the 4 buses? The 4 buses include this one we have joined, which is 1 ohm. These two join, another 1 ohm. This one over there, and this one over there. This is 1 ohm. They are now all in series. Total now becomes 1 plus 1 plus 1, and that one that gives us a total of 4 ohms. So this is the equivalent of the net resistance. So we'll go to another problem that is obtained from WAEC examination. We have the diagram. This is 3 ohm, 6 ohm, and then we have a battery down there. Then that is it. We are asked, they say, if the current across the 6 ohm resistor is 1.5 amperes, calculate the current in the 3 ohm resistors. So if the current in the 6 ohm resistor is 1.5 amperes, calculate the current in the 3 ohm resistors. So let's look at the problem on the board. This is the battery, and we'll look at the equation. The battery is in series with the 6 ohm resistor. That means the current coming out from the battery is actually 1.5 amperes. As I said before, when instruments are connected in series, the same amount of current will flow through them. So the current coming from the battery will be the current that flows through the 6 ohm because the battery and the 6 ohm resistor are in series. But when the current reaches this point, it's going to break into 2. So let's look at it this way. So we can see the 1.5 ampere either from this end or this end. On reaching this point, we have 3 ohm resistor here. I have also another 3 ohm resistor. On reaching this point, the current splits into 2. Here we have into I1 and I2. The current splits into 2, but 2 raised into 2. So for us to find I1 and I2, we have to find the potential difference across the 3 ohm resistors. And remember, when resistors are connected in parallel, they will have the same potential difference across them. So how do we go about this? We now have, from this illustration, 1.5 is equal to I1 plus I2. So this current breaks into 2. And from Ohm's law, current is voltage over resistance. So we can now say 1.5 equal to V over R1 plus V over R2. Because the voltage across the resistors remain the same. So now I have 1.5 equal to V over our R1 is 3 and our R2 is so the same 3. We take LC and that is 3. 3 into 3 is 1 times V gives you V. 1 times it gives us V, which is 1.5. Cross multiply, we have 4.5 equal to 2V. So our V becomes 4.5 all over 2, which is 2.25 volts. So the current in each of the resistors, V over R1 or V over R2, since the two of them are equal, will now become 2.25 over, since our R1 or R2 is 3, all over 3. So current now becomes, to divide, have 0.75 amperes. So the current flowing through each of the 3 ohm resistor is 0.75 amperes. We have a diagram, circuit diagram. This is the ammeter reading 0.4 ampere, and the ammeter is in series with the resistor of 4 ohms and the battery. That means the current in the ammeter register is the current coming out from the battery, which will also pass through the 4 ohm resistor. Then, but on reaching here, this current will split into 2 because these two are in parallel. R and 2 ohm, these external resistors are in parallel with the battery, while this one is in series with the battery. Now let's go to the equation. It's an SSC equation that says neglecting the resistance of the cell. That is, we should neglect the internal resistance of the cell. So small r is going to be 0. Calculate the value of big R, that is internal resistance, in the circuit diagram. So how do we solve this problem? We use the circuit equation I equal to E all over R plus small r. And mind you, the value of small r is already taken as 0. They say we should neglect it. So our E is 2 volts. So E is 2 volts. Then our I, current coming out from the battery, is our I, which is 0.4 amperes. Our big R is obtained by combining this total of the external resistance, combining up this and that. And as I told you, when you have 2 resistors in parallel, the simple way to combine them is to take their products and divide by their sum. That is 2 times R all over 2 plus R. Plus, this one is in series, which is 4 ohm. So when we solve this, that gives us 2R all over 2 plus R, then plus 4. So this is the total of the resistance here. This is total external resistance. So, having done that, we go to the formula and make substitution. The value of our I is 0.4 equal to the value of our EMF is 2 volts, which we wrote down here. All over the value of our big R, which is total external, is this expression 2R all over 2 plus R, then plus 4, which will solve out there. The value of our small r is 0 because the battery has no internal resistance. So there is no internal resistance, which we have to neglect in the equation. So making this substitution, we now cross multiply. We now have 0.4 bracket 2r plus 2 plus r plus 4 equal to 2. If you open the bracket, you have 0.8r over 2 plus r equal, okay, plus this multiply this, that gives you that. This multiplied with that give us 1.6 equal to 2. Collecting like terms, 0.8 r all over 2 plus r. This crossing becomes 2 minus this, giving us 0.4. That is it. Then we now cross multiply once more. Carrying this one to that side, we now have 0.8r equal to 0.4 into 2 plus r. Open the bracket, 0.8r equal to 0.8 plus 0.4r. Taking like terms, crossing over, 0.8r minus 0.4r equal to 0.8. Subtract, we have 0.4r equal to 0.8. R now becomes 0.8 over 0.4. To divide, the answer is 2 or 2 ohms. So the correct answer to this question is option B, which is 2 ohms. That's the value of the external resistor. You take a look at our working and understand what we have done.